Department of Mathematics Trishur, and all the participants, a heartfelt welcome to Ms. Lexi Alexander. Welcome, ma'am. And we will start the session on block ciphers, design and analysis. Thank you.
Thank you, Vijay, for the introduction. I thank the Department of Mathematics at Thomas College for inviting me for this workshop. So I am very glad to give you the lecture. Actually what Vijay announced, I have a little change I made in the topic. So earlier I had seen your talks, they were on block cipher, AES design, and differential cryptanalysis and all. So I thought I should not talk again on the same thing like block cipher design and analysis. So I am talking about, so you've seen a design which is AES, Advanced Encryption Standard, and also a classical cryptanalysis, like a differential cryptanalysis on the block ciphers. So today now I'm planning to cover quantum cryptanalysis on AES. So there is only one attack which is as of now reported for AES, which is Grover's search attack. So my talk is on that only. So sorry for the change in topic. So I will share my presentation. Can you see the presentation?
Yes, it is visible.
Yeah. It's in full screen, no?
Yes, but
Okay.
you have to start slideshow.
I am already showing full screen on a slideshow only it is. Okay, shall I start?
Of course, of course.
Okay, so Grover's attack. So this is different from our what we are familiar with, the classical computational theory. So we are going to do attacks using quantum computers. We are going to use quantum computational theory. So I'm telling about some basics of quantum computation theory here. So like in the classical thing, you have bits. They are either 0 or 1. Only two values only it will take. But in case of quantum computer, the basic information quantity is a qubit. So it is called a qubit instead of classical bit. It is qubit, quantum bit, like that, qubit. So qubit, mathematically we can tell it is as a set of all ordered pairs, alpha, beta, where alpha and beta are complex numbers such that mod alpha qubit. So classically it is 0 and 1. So you can understand classical bit 0 is mapped as the vector 1, 0, and classical bit kind of 1, which is mapped as vector 0, 1. So vector 1, 0 in a qubit, it is denoted by ket. This notation is read as ket 0, and 0, 1 is read as ket 1. So any alpha beta, any vector alpha beta, we can write it as alpha into 1, 0 plus beta into 0, 1. So that is a usual mathematical notation in terms of basis. So that means the state of a qubit usually denoted by the notation ket psi. So ket psi is equal to alpha ket 0 plus beta ket 1.
Excuse me.
So this is written as like this. That is state of a qubit. psi is written as alpha ket 0 beta 1. It is yeah.
Yes, it's not moving.
Okay, slide.
Yes.
Now.
So
To share computer screen, not a window. Okay. So a qubit is therefore are complex numbers with the condition that mod plus mod beta square is 1. So we can write, if we denote that vector 1 as ket0 and vector 0 1 as ket1, then we can any alpha beta alpha into 1 0 plus beta into 0 1. That is the state of the qubit. Ket psi is written as a linear combination of ket 0 and ket 1. So, and alpha beta are varying over complex numbers. So, unlike the classical bit, which takes only 0 and 1, a quantum bit qubit can take infinite number of states. So, as alpha and beta has infinite number of choices, but with the condition mod alpha square plus mod beta square is equal to 1. But they have infinite number of choices. So, a qubit has infinite number of states. For a particular value of alpha and beta, it will give a state. So we will always tell that a qubit is always in a superposition of ket0 and ket1. So ket0 and ket1 are taken as the basis states. So it is a linear combination of ket0 and ket1. So linear combination, usually physics people tell it as superposition. So superposition of basis states ket0 and ket1. So other than ket0 and ket1, some other bases are also possible. We can represent in that way also. So physical representation, photon is considered as all possible polarization states of a photon. So if you take a photon, its polarization, it has infinite number of possibilities. So one that represent a qubit or a spin of the electron, that is also represented as a qubit. That is a physical representation of the qubit. So mathematically, you can consider it as an ordered pair of complex numbers. So if you take some other basis, suppose I am taking, so this basis is denoted by ket plus. So that is actually equal to 1 by square root of 2 ket0 plus 1 by square root of 2 ket1 and minus 1. Ket minus is 1 by square root of 2 ket0 minus 1 by root 2 ket1. So this h is equal to, h is equal to ket plus minus. That is not 0 1. Ket plus and ket minus. It is called the Hadamard basis. So if ket psi is equal to alpha ket 0 plus beta ket 1, then in terms of ket plus and ket minus, we can write it as alpha plus beta by square root of 2 ket plus alpha minus beta by square root of 2 ket minus. So it has qubit can be represented with respect to different bases also. So accordingly the coefficients will keep changing. So and change of basis from one base to another, all those things we can in linear algebra. So most of the things are basic linear algebra you have to use to do this quantum computing. So now we have this infinite number of states. So how we will find out which state the qubit is? So actually it is not possible for us to find out which state exactly the qubit is. So how to measure either in one of these bases? So once you represent the qubit, you have to measure one of the bases. So which base you are measuring, and side is projected mapped in that direction, and will give only that coefficient. Okay, so if your ket psi is equal to alpha ket 0 plus beta ket 1, and you have to measure either along the direction of ket 0 or along the direction of ket 1. You cannot measure both together. This is because of the uncertainty principle of Heisenberg. So you can't measure momentum and the speed at the same time. Correct? So we can measure only in one direction. Then next time when you try to measure the other direction, the state will change. So when you measure in along the zero, ket 0, you will get the output ket 0 with the probability its amplitude square. So its amplitude is alpha here. So mod alpha square. So complex numbers, you have to take mod alpha square. And probability you will get 1 is the coefficient of beta 1 is beta. So mod beta square. So total probability is 1. Mod alpha square plus mod beta square is equal to 1. So you have to measure. So this is a classical measurement. So we can measure only through classical way. So you have to measure through any of the basis vectors. So when you measure through that, you will observe that outcome with its amplitudes modulus amplitude square. That is the probability. So outcome of a quantum computer, when you measure an qubit, you will always get a probabilistic result. It is not a deterministic result, unlike a classical computer. So classical computer, if you measure 0, it will be 0. Anytime, any number of times you measure, it will be always 0. 0 you measure, always it will be 0. 1 you measure, always it will be 1. But in case of a quantum qubit, it is a probabilistic output. You will get 0, ket 0 with the probability mod alpha square, and you will get ket 1 with the probability mod beta square. Okay. So now suppose we have two qubits. So two qubits, I had taken the states as ket psi 1 and ket psi 2. So ket psi 1 is equal to some alpha ket 0 plus beta ket 1. And ket psi 2 is some gamma ket 0 plus delta ket 1. So we have here two qubits. So we consider them together as one single system. So state of the two qubit system is ket psi 1 psi 2. Together we will write ket psi 1 psi 2. So it will come as the tensor product, Kronecker product of all the states. So it will have ket psi 1 tensor ket psi 2. So how we will compute that? Alpha ket 0 plus beta ket 1 tensor gamma ket 0 plus delta ket 1. To compute this, it will be equal to alpha gamma ket 1 plus beta delta gamma ket 1 0 plus beta delta ket 1 1. So here you can actually verify that beta gamma square. When you have two qubits, there are four possible states. First can be 0, second qubit can be 0. So that is the state 0 0. That will be coming with the then first qubit can be 0, second qubit can be in 1. So that is ket 0 1 state. So probability of that ket 0 1 you measuring the output is mod alpha delta square. Now it can be first qubit can be in 1 and second qubit can be in 0. Gamma square. You get outcome mod alpha delta square. square is equal to 1. So this is the condition for a general 2-qubit system. So unlike we derived like earlier as a tensor product of two single qubits, all 2-qubit systems write as a tensor product of single qubits. So for example, suppose this is a qubit state. Mod get 5 plus is equal to 1 by square root of 2. Get 0, 0 plus get 1, 1. So this is a valid qubit state, but this you cannot write as a tensor product of two single qubits. So this is called special, it is called a Bell state, and it is an entangled state. So this we cannot generate as a tensor product. This is generated using some other quantum gates. So using some Hadamard gate and a C0 gate. So I will explain that later on. What are these gates? So this is general. This is the formula, but it is not always a tensor product of two single qubits. Other than that, also we can have different states. So now we go to 3-qubit state. So 3 qubits means there are 8 possible basic components. That is 0, 0, 0, 0, 1, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. So this will written as a linear combination of all the states. So catus I, we will write it as A. So short, we can write it as instead of A000, you can write it as A0 itself. So A0, ket 0, 0, 0, plus A1, ket 0, 0, 1, plus A2, ket 0, 1, 0, plus A3, ket 0, 1, 1, plus A4, ket 1, 0, 0, etc. Like that, plus A7, ket 1, 1, 1. So here also this condition should be there, that whatever is their amplitudes, how many number of the sum of their modular squares should be equal to 1, because that is representing actually the probabilities of measuring that particular component vector. Now, if you have multiple qubit systems, suppose there are n qubits, then in a similar way, we will get actually 2 power n different component states. So get 0, 0, 0, like n zeros, and get 0, 0, 0, n minus 1 zeros and 1, etc. Like that, get all n ones. So all coefficients are represented as A0, A1, etc., A2 power n minus 1. And so their sum modulus square sum should be equal to 1. So that is what we are telling. If we have n qubits, you can have a linear combination of 2 power n states. So a qubit, n qubit, can represent any number between 0 to 2 power n minus 1, and it can do all these calculations together. That is the difference between the classical n bits and n qubits. So now we have qubits. So now we have what we have to do. We have a quantum computer, and there so many qubits are there, and then we have to transfer the qubits. Then only we are doing some operations on the qubits. So that they are called quantum transformations. That is, we are applying something on some transformations on the qubits and changing its states to some other states. So actually, the quantum transformations are all unitary transformations. Because why? Because the length has to be preserved. The length that what we are telling, that we are taking the sum of all modulus square sum we are taking. So that length of this vector A0 to A2 power n minus 1 is always 1. So that length has to be preserved even after transformation. Resulting vector also should satisfy the same condition. So only unitary operations, unitary operators, unitary transformations only guarantee this. So all quantum transformations are unitary transformations. So what you mean by unitary transformation is, you know that already. So a transformation is T is unitary if and only if T star is equal to I. T is the identity matrix and T star is Hermitian, the complex conjugate. Transpose complex conjugate of the T. So all matrix representation, any unitary transformation, we can take it as a quantum transformation, and all quantum transformations are unitary transformations. So we have a matrix representation for all the transformations. So we will one by one see all the transformations. First one is a single qubit quantum gates. So in classical thing, we have only one gate which act on a single bit. That is the NOT gate. So which flip the bit. So if 0 is the input, the NOT gate will split into 1. If 1 is the input, it will give the output as 0, the NOT gate. But in the quantum scenario, we have many number of single qubit gates. So first category of sets is that poly gates. So there are poly X gate, poly Y gate, and poly EZ gate. So what X gate is doing is, so in quantum circuit, we will represent this gate as like this. So input is coming from left, the gate is represented in a box. What is the name of the gate? We'll write inside the box, and output is towards the right side. So always quantum circuit, we will write input on the left, output on the right. And its corresponding matrix is 0, 1, 1, 0. So that is means what this matrix is a unitary matrix. So it is a valid quantum gate. Now next one is Y gate. So Y gate representation is like this in the quantum circuit, and corresponding matrix is 0, 1, minus 1, 0. So this is again a unitary matrix. And EZ gate, the corresponding matrix is 1, 0, 0, minus 1. So if you see the matrix X corresponding to X, so X is actually doing negation, which is similar to the not classical NOT gate. So if you multiply 0, you will get 1. So if you multiply with the 1 vector, then you will get 0. So X transforms 0 to 1 and 1 to 0. Now you see EZ what it is doing. So if you multiply with 0 thing, 1 0 is going to 1 0 itself. So that is 0 is going to 0 itself. And if 1 is there, that is 0 1, if you multiply, you will get 0 minus 1. That is minus of K2 1. So K2 1 will be transformed to minus K2 1. So that means it is changing the phase of the amplitude. So amplitude, if it is positive, it became negative. If it is negative, it will become positive. So like that. So 0 is not change for 0, but K2 1 will be changed to minus K2 1. And Y you can verify it is equal to Z into X. So K2 0 will go to minus K2 1, and K2 1 will go to K2 0 under Y. So another important single qubit quantum gate is Hadamard gate. So Hadamard gate is denoted by H. So its matrix is 1 by square root of 2, 1, 1, 1 minus 1. So this is also known as quantum Fourier transformation. So this is same formula like Fourier transformation formula in the classical thing, but it operates in a different way in the case of quantum. So if you have the K0 vector, so that is the vector 1, 0. So you multiply with this matrix, what you are getting result is 1 by square root of 2, K0 plus K2 1. And if you take K2 1, that is corresponding vector is 0, 1. So if you apply the Hadamard matrix, you will get the result as 1 by square root of 2, K0 minus K2 1. Okay. So now we have S gate. So S gate representation is like this. In the box, we will write S, and corresponding matrix is 1, 0, 0, I. So in this case, K0 is mapped to K0 itself, and K2 1 will be mapped to I K2 1. And T gate is also very important. It is doing some rotation. So its matrix is 1, 0, 0, e power I pi by 4. So it K0 will be always mapped to K0 itself, but K2 1 will be rotated by one angle pi by 4. Now next we will go to 2 qubit quantum gates. So the quantum gates which is applied on 2 qubits. So the famous example is C0 gate. It is also known as CX gate. That it is doing controlled NOT. C means stands for controlled NOT gate. So if you have a qubit, so it is a 2 qubit system. So we have A00 Ket00 plus A01 Ket01 plus A10 Ket10 plus A11 Ket11 into what it is doing. So it is easy. Actually, you see the first qubit. If it is 0, it will not do any change. So A0000 will map to itself. A01 Ket01 will be mapped to itself. But if first qubit is 1, it will flip the second qubit. So A1010 will be mapped to A1011, and A1111 K211 will be mapped to A11 K210. So that is what it is. The matrix is like this. So first 2 qubits, it will be same like this. Second one will be flipped. So its column will be 0001, and third one will be the flipped one. So it will be again 0010. So C0 gate matrix representation is like this. So A00, A01, A10, A11 will be mapped to A00, A01, A11, A10. So in gate, it is represented like this. So 2 qubits are coming, A and B as input. First qubit is output is like that only. Second qubit is controlled. So if it is equal to 0, B only will be coming out. So A XOR B. If A is equal to 1, then it will be 1 XOR B. It will be complementary. So in quantum circuit, this is the notation which is used, 1 dot and an XOR. So it is equivalent to the XOR operation in the classical gate. Then 3 qubit quantum gate. So this is known as Toffoli gate, which is controlled C0 gate. So again C0 gate, one more control bit will come. So 2 controls A and B acting on the third qubit C. So what it will do, whenever both A and B are 1, then only C is flipped. Otherwise C is unchanged. So different values of I have written A and B. So A, B and C, all 8 combinations. So till up to the last, all input output is same. So for the last two only, A and B are both 1. So in that case, C will be flipped. That is 110 will be mapped to 111, and 111 will be mapped to 110. So this is equivalent to the AND gate. So if we initialize C is equal to 0, so whatever be the input with A and B, so what in the output in C, what you are getting is AB. That is A and B. The AND gate, it is implemented. So in classical world, that AND gate, the XOR gate, these are all not invertible. But in the quantum case, these all gates are invertible. They are denoted as unitary transformations, and they are invertible. So you can see that in all quantum gates, all quantum gates are unitary transformations, and so they are always invertible. Unlike classical gates, which are most of them are not invertible. Next one is a Clifford group of quantum gates. So it is introduced by Daniel Gottsman. So it is named after the mathematician W.K. Clifford. So why Clifford group has brought this? There are so many quantum gates, but some of them are too much error propagating. Means when you apply these gates, always some errors will be added up, because we are working with very atomic particles. So errors will be added up. So some gates will always introduce more errors. So as you keep applying, your output will be so much deviated from the desired output. So those kind of gates are not usually used for implementation. So for implementation, we want a fault tolerating quantum circuit. So that is what we want, the quantum gates which will minimize the error propagation. So that's a particular set of quantum gates. They are considered as a Clifford group. So Clifford group of quantum gates, they are fault tolerating quantum gates. So the group is generated by this set, S, H, and C naught. So this is like your generator of the group, and all these combinations of these things now will generate the other gates. So S, H, and C naught will generate other gates, so many other gates which we mostly need in our implementations. So this S, H, C naught is known as generators. And quantum circuits always implemented using this gates S, H, and C naught along with the T gate. So T gate is not generated by S, H, and C naught. So plus T gate also we have to add. Now whatever all that poly gates gates. So I said what we defined. All can be generated using this SH and C. So usually the Clifford group along with the T gate, that is actually called as the quantum universal gate set. So in the classical scenario, we have the NAND gate, which is a universal classical gate. So any combination of NAND gate, you can represent all other gates in terms of NAND gates. But in case of quantum scenario, we don't have a single universal gate. So no gate can alone generate other gates. So here we have a combination, collection of generator set, which only will generate other all quantum set. So it is Clifford group plus T gate. So you always see in the literature like Clifford plus T gates are used. Means that this is what it means, that the Clifford set along with the T gate is only used for implementation. So why we want is because we want a fault tolerating quantum circuit. Now, what is meant by equal superposition of qubits? So any linear combination of qubits, that is a linear combination, is superposition. So if some qubits are in zero state, we can convert them into equal superposition. Equal superposition means all the component states have the same probability of occurring. So that is usually achieved by using Hadamard gate. So Hadamard matrix we define using the recursive formula. No? So first one is H0 is equal to 1. Then for HM, for M greater than 0, HM is equal to HM minus 1, HM minus 1, HM minus 1, minus HM minus 1. So its degree will increase in power of 2. So second one, H2, which we usually denote as H capital H in our circuit, H2 is equal to 1, 1, 1 minus 1. Then H tensor 2 is H tensor H. So that is 1, 1, 1 minus. So H will come here in place of 1. In place of 1, again H will come. In place of 1, H will come. In place of minus 1, minus H will come. So like that, H tensor N also we can define, which is like tensor product of H N times. So in N qubit system, that is, this is get 0, 0, 0. If you apply, you will get 1 by square root of 2 power n. This to make the probability 1, that amplitude everywhere it will be equal. So summation I equal to 0 to 2 power n minus 1 get I will get. So now every component state has the same probability 1 by 2 power n. So if we initialize the initial states to 0 and then apply Hadamard, you will get equal superposition of qubits. Now, any function, anything in the classical thing, when you implement, it is implemented as a Boolean function. So, Boolean function f on n variable, n inputs, it's a mapping from 0, 1, n, the set 0, 1, n to 0, 1. So, it inputs taking value only 0 and 1, and output is either 0 or 1. So, in a quantum computer, how you will implement this? Because this is mapping to n to many to 1, many to only 0 and 1. So it is not invertible. So what we will do is, in a quantum computer, it is implemented using a transformation which is called UF. And it is implemented on n plus 1 qubits. Instead of n qubits, we have to take n plus 1 qubits to make the circuit invertible. So whatever inputs that get x, n qubits, we will give here. All x belong to f2 power n, n qubit input state will be given, plus 1 target qubit. This single qubit, these are n qubits and one is single qubit. That's why n plus 1 qubits. It will give output also will be n plus 1 qubits. So it will compute whatever input is there, it will give just like that itself, and whatever the function value is calculated, which will be XORed to the target qubit. So there one C0 gate will be used inside this. So what you will get is x and get x and get y XOR f of x. So this become an invertible case, no? And this is become a unitary transformation also. So this is how a Boolean function is implemented. It is usually denoted by this function UF. So now a quantum circuit, how it look like? So I give an example. So this is a quantum circuit. So here 3 qubits are given as input, get 0, get 0, get 0, all initialized to 0. So always most of the algorithms what we use, we initialize all the qubits to 0. It is easy to achieve because we have to make the temperature into 0 Kelvin almost. All the qubits will go into the ground state, 0 state. So usually the algorithm starts like that only. And here one Hadamard gate is applied. Then in the third qubit also one Hadamard gate is applied. Then output of first qubit is taken, and then the C0 gate is applied to second. Then say is that one output is taken and applied a qubit C0 on the second, third one. Then we have T gate on the second and third qubits. Then we have another C0 from third to second qubit. Then another C0 from first to second qubit. Then 3 Hadamard gates applied on first, second, third qubits. Then an S gate applied on the first qubit. And this is how we have taken this as the, after this many operation, the state of the qubit. This system is taken as get sign. So here you see how many gates are used. The total number of T gates. There are only 2 T gates, correct? Now there is another concept called depth. So depth means how many operations you can compute. You have to come, how many time steps are required to reach the output. So here what will happen, this H and H, they are operating on independent qubits, first to H. So this can be done in parallel. So this has taken as a single count, single depth. And then only this, after this H only we can apply this C0. So this becomes the second step. After this C0 only we can apply this another from second to third one. So this becomes the third step. Now we have 2 T gates here. This is together parallel. We can apply. This is operated on independent qubits. So this will become 1, 2, 3. Now fourth step. Then this C0, it will apply because it is on this. So fifth, and after that only this one will come. So this is become sixth. And this H are all in the parallel. So 7. And this after this only S can be applied. So 8. So there are 8 time instances. So we tell it as full depth is 8. Means 8 gates are there to pass through. Now number of T gates is 2, but its depth is 1 because both the T gates are applied in parallel. So its depth is 1. Number of H gates is here 1, 2 here and here 3. So total 5. But depth is 2 because these 2 are applied in parallel, but these 2 are applied in separate, different instance parallelly. So total 2 instances of H gates. So total H depth is 2. So number of T gates is 2, but T depth is 1 here. Number of H gates is 5 and H depth is 2. And full depth is 8 here. So this is very important parameter when you compute the strength, complexity of the circuit. So usually complexity of circuit is told by counting the number of gates. So we will count the Clifford gates and we will count the T gates. We will count how much is the depth of the circuit, how much is T depth, how much H depth, like that we will tell. So there is a command in Qiskit. So Qiskit is a software which acts as a interface between the IBM quantum simulator and IBM quantum computer. So you write a program in Qiskit and you can run that in the quantum simulator or quantum computer. So this in Qiskit there is a command when you write the program for one circuit. So it will use this command, quantum circuit dot depth bracket that function name. Then you will get the values of these things. So circuit depth is smallest number of steps required to perform the circuit, and if every gate is operated at integer time steps, that is how we assume. Now gate which act on no common qubits are allowed to perform at the same time. Step, so gate acting on at least one qubit in common must act at different time steps. So now, so we consider all gate one by one, and then we compute how much it is contributing to the length and the longest path till we reach the output qubit. So I think you understood what is meant by quantum circuit and how we compute the depth. So now once we have quantum circuit and we know how to implement. So there are quantum algorithms. There are many quantum algorithms. The first quantum algorithm which was reported is by Deutsch-Josua algorithm, then Bernstein-Wairani algorithm, Shor algorithm, Grover's search algorithm, Simon's quantum algorithm. Like that, now so many quantum algorithms are coming. So here I am not explaining all these algorithms. We are focusing only on Grover's search algorithm. So before going into Grover's search algorithm, so NIST has given some bounds on maximum circuit depth. So we are implementing a quantum attack. We are implementing designing an attack. So this Grover search algorithm is a quantum algorithm which has to be implemented on a quantum circuit. So how much the circuit can become. So you can write a big program which will never complete and finish. Correct. So that is why NIST has given some bounds on the circuit depth. What can be the maximum circuit depth for any quantum attack? So that parameter they had called as max depth. So max depth. So this restriction is motivated by the difficulty of running extremely long serial computations in a quantum computer because of the error propagating properties of these gates. So this NIST has proposed the values of max depth from 2 power 40 to 2 power 96. So max depth 2 power 40 means it is equal to the approximate number of logical gates that presently envisioned quantum computing architectures can expected to serially perform in a year. So NIST is telling that in a year, quantum computer, as per present architecture, can perform 2 power 40, that circuit length of size 2 power 40. So it will take 1 year. So if you, and that attack will take 1 year to recover the key. So it will give only 1 year cover time for your secret information. Now, max depth 2 power 64 means approximate number of logical gates that current classical computing architectures can perform serially in a decade. So this will give a security in a decade. For a 10 year security, the max depth of the attack should be 2 power 64 or more. Then 2 power 96 max depth 2 power 96 means it is approximate number of logical gates that atomic scale qubits with the speed of light propagation times could perform in a millennium. So this is actually they consider as a millennium security. So 2 power 96. So accordingly, NIST has given some security classification. So there are 1 to 6 security levels, level 1 to level 6. So it is done in terms of max depth and all, and total gates in the circuit. So all those things they had defined in terms of comparing the strength of AES and SHA-3 standard. The key recovery attack on AES and collision attack on SHA-3 is taken, and circuit depth is limited to max depth. So it is between 2 power 40 to 2 power 96. So level 1 security, it is compared to the security of AES 128. So what are the resource estimates? It should be 2 power 170 per max depth quantum gates, or 2 power 143 in classical gates comparison they made. Now level 2, it is equivalent to the security of SHA-3 256. So which need 2 power 146 classical gates as of now. And level 3 means security of AES 192, which is defined as 2 power 233 per max depth quantum gates, or 2 power 207 classical gates. And security level 4 is for SHA-3, and security level 5 is for AES 256, and security level 6 is SHA-3 512, which needs 2 power 274 classical gates. So level 6 is also known as a very paranoid security, because maximum AES 256 that we are telling it. Now here what Grover's algorithm is doing. So this is a generic algorithm. Grover's algorithm is a generic algorithm which gives solution to the search problem. Search problem is always related to the brute force attack. So what we have is we have an unsorted database which contains n items. In that, only one item satisfies a given condition. So that item we have to take it. We have to identify which is that item. So once that item is one, so what we have to do? We have an unsorted, so we have to take items one by one and examine the item and tell whether it satisfies the condition or not. So the algorithm assumes that this can be done in one step, but it cannot do any sorting on the database that will help in the selection. So the most efficient classical algorithm for this is to examine the items in the database one by one. Once you get an item which satisfies the required condition, you stop. Otherwise, you keep aside that item and take another item from the set. Again, check whether the condition is satisfied. If it is satisfied, you are done. Otherwise, you have to keep it apart and take another one like that. So in brute force attack also we do the same thing. No? We have a bunch of keys. We don't know which is the correct key. We will try one by one till we get the correct key. So wrong key we will not try again. No? We will try one by one. So in classical sense, how many number of steps it will take? So the average number of steps required will be 1 plus 2 plus extra n divided by n. So correct. It can be in the first attempt itself. So it is 1. It can be the second attempt. So it will be given 2, or it can go up to the nth item. It can be the last item. So average would be 1 plus 2 plus etc plus n divided by n items. So this will give n plus 1 by 2. So it is a function in n. So we will tell on average this will take a big O of n steps. So this is computer scientist notation big O of n. So that means it will on roughly take n steps kind of. So if n is equal to 2 power n, like in our case for key search, suppose A is key search you have to do. So it is 128 bit length. So total size is capital N is in this case is 2 power 128. So then the average number of steps required is again order of 2 power 128, order 2 power n. So this is very huge. So in class using classical computer, you cannot do the search problem. You cannot exhaustively search this. But now Grover's algorithm, which is a quantum algorithm, we can do much better. So this is introduced by L.V. Grover in 1996. He is an Indian mathematician. So quantum algorithm, it is a quantum algorithm for searching unsorted database. And it takes order of square root of n steps in a quantum computer. So the complexity if n is equal to power n is order of 2 power n by 2. So this is actually reduced into quadratic reduction. So it became too much reduction in this case. So you see in case of A is 128, classically we have to search 2 power 128 on average. Now we have to search only 2 power 64. So this 2 power 64 and 2 power 128, too much differences. So it's given a quadratic reduction. So this is the quantum block diagram of Grover's algorithm. So we have n qubits. So A is 128, you have to search. Then n should be 128. So 128 qubits in the first line. So that is shown a single line, but it is n qubits are there, n lines are there. So n zeros all initialized first to 0. Then you have to apply the n 2 power n by 2 power n Hadamard matrix. And for one also you are applying the Hadamard matrix, the target qubit, and then the operator which implementing AES as a Boolean function. So that U omega, it will come. Then there are some operations which is called as Grover diffusion operator, and it is iterated order of square root of n times, and finally from the last n qubits we will measure. That is the classical measurement. Then you will get the correct key with very high probability. So how that is working we will see now. So any doubt is there till now?
you have any doubt, please be free to ask.
Okay, now we will go to the algorithm, Grover search algorithm. So the problem definition we already seen, that is, we have a system in that any power n states are there. So the states are labeled as S1, S2, etc. Sn. These 2 power n states are represented by n bit strings. We have seen that, and there is a unique state SV that satisfies the condition. So C SV is equal to 1, whereas for all other states CS is equal to 0. So assume that for any state, the condition CS equal to 0 can be evaluated in unit time. So now our problem is we have to identify which is that state. So what are the steps now? First, you have the initialization state, which all states are in 0. Then we will make it into an equal distribution system. So that we are applying the Hadamard gate. So everybody will have the amplitude equal to 1 by square root of n. So all n qubits, n system, n linear combinations will have 1 by square root of n. Now we have to repeat the following 2 steps, pi by 4 square root of n times. That order of square root of n, actual value is the floor of pi by 4 into square root of n. So first we have to, so here is the quantum, this step. Everywhere these steps and all other steps you can do in classical computer also. So where is the quantum effect is used? Quantum effect is used in the second step A, second A steps. So we have n qubits which are in superposition. So the quantum computer will apply that UW function on all these n qubits, and at the same time parallelly compute for each of these component vectors. That is, there are 2 power n component vectors, the corresponding output. So the value of C, the condition it will check, it will compute, and where it get 1, there it will rotate its phase by pi radians. Remaining all amplitudes will get unaltered. It will not change anything. So only which component where it will get CS equal to 1, for that amplitude will be rotated by pi radians. That amplitude will become minus, negative will be. Remaining everything will be unaltered. After that, you apply a diffusion operation. So diffusion operation will be applied. So that is again unitary matrix D. So it is defined as Dij is equal to 2 by n if I is not equal to j, and Dii, the diagonal entries are equal to minus 1 plus 2 by n. That is, all off diagonal entries are 2 by n, and all diagonal entries are minus 1 plus 2 by n. So this D also we can implement. This is a different gate, no? So but this D can be implemented using that Hadamard gate and one rotation. So D can be written as that 2 power n by 2 power n Hadamard matrix H tensor n. And so into R into again H tensor n. So R is the rotation matrix, and it is defined as Rij is equal to 0 if I is not equal to j, and Rii equal to 1 if I equal to 0, and Rii is equal to minus 1 if I not equal to 0. That is, R is a diagonal matrix. R is a diagonal matrix in which first diagonal entry is 1, rest of the diagonal elements are minus 1. So that is also a simple matrix to implement. So after repeating that pi by 4 square root of n times, then we measure the state. Then we will get the correct, that unique state SV with the probability at least half. So this is the Grover algorithm steps. So I will show with an example, then you will get more insight into it. So this is a small tiny example. Suppose we have n is equal to 8 items. So states are I represented as a binary representation 0 to 7. No? So 0, 0, 0, 0, 0, 1 like that up to 1, 1, 1. Binary representation. So 0 to 7. So suppose your marked state is 1, 0, 0. So which we need to identify using the Grover's algorithm. No? So we don't know, it will come as output of Grover's algorithm. So how it is coming? So first we have to take n is equal to 3, that is log 2 of capital N. So that many qubits, and we have to prepare a 3 qubit system with initial state. Initial state, all 3 qubits are 0, 0, 0, 0. Okay, so corresponding amplitude vector will be 1 and 7 zeros. Correct. Now we have to make an equal superposition of these steps. This is the first step. So we will get a new state, which is psi1, which is 3 times tensor product of H into psi0. So 3 times tensor product of H, the Hadamard matrix will be equal to like this, 1 by square root of H, and this is the Hadamard matrix. So we multiply with that amplitude vector. So corresponding to 1, 0, 0, only one vector is there, is that one amplitude is 1, rest nothing is present, so all the things are 0. So now you multiply, so it is only first row only will come, rest everywhere it will be, first column only will come out, rest everywhere things 0. So it will be equal to 1 by square root of it, all 1, 1, 1. So the state of psi1 is equal to now 1 by square root of it. For get 0, 0, 0, it is 1, get 0, 0, 1, everything will come equally. So all will have same amplitude 1 by square root of it. So you can see 1 by square root of it, modulus 1 by square root of it square 8 times. It will be equal to 1. So after this is the equal superposition of 3 qubits. Now what we have to do? We have to apply the oracle UW. So it will compute. So I cannot show it over here. It will compute on all the inputs, and then which is that state which gives CS equal to 1. It will flip its amplitude. So this is the it is the fifth element. So fifth element, it will be -1 for flipping. Rest everything unaltered. So it will be 1, 1, 1. So this is like an additive matrix. So it will flip only -1. So 1 by square root of it, 1, 1, 1, 1. Then -1, 1, 1, 1 will come. So this is done quantum computer, quantum parallelism one thing is there. So because of that, it will compute all together at time in the linear combination, and then it will give the output like this. So this is the quantum phenomena is used over here. So this we cannot do in classical computer. And the new state psi2 now will be equal to 1 by square root of it. So here ket 0, 0, 0, ket 0, 0, 1, ket 0, 1, 0, ket 0, 1, 1. But for 1, 0, 0, it now amplitude rotated by pi degrees. So 1 become -1. -1, -1, 0, 0, plus 1, 0, 1, plus 1, 1, 0, plus 1, 1, 1. So now we have to apply the diffusion operator. So that is actually all the off diagonal entries are 2 by n, and all the diagonal entries are 2 by n minus 1. So it is like this. Here some. So you have to just all diagonal off diagonal entries are 2 by n, rest of diagonal entries are 2 by 8 minus 1. So you apply that to the next amplitude vector, that is 1 by square root of it, 1, 1, 1, 1, minus 1, 1, 1. So what you will get is as 1 by 2 square root of it, 1, 1, 1, 1, 5, 1, 1, 1. So the new state will be psi3 is equal to 1 by 2 square root of it. All everywhere it is plus 1, here only will become 5. So what is the probability of now measuring 1, 0, 0? It will be its amplitude square, that is it is 5 by 2 square root of 8 modulus square, that is 25 by 4 into 8, which becomes 0.78125. It increased, other things are decreased now. Other states, the probability is decreased, and for 1, 0, 0, it is increasing. So now we have to iterate it again. So the oracle again computes UW again like this, and it will flip that amplitude. So we have that amplitude now 1 by 2 square root of 8, 1, 1, 1, 1, and 5, 1, 1, 1. So there we will flip that amplitude. So 5 will change it to -5. So this will become the new state. In that 5 will change it to -5. Rest everything will be the same. Now again we have to apply the diffusion operator. So it is same matrix, that is every of diagonal entries are 2 by 8, and all diagonal entries are 2 by 8 minus 1. So when you apply to this new amplitude 1 by 2 square root of 8, 1, 1, 1, 1 minus 5, 1, 1, 1, 1, you will get 1 by 4 square root of 8, minus 1, minus 1, minus 1, minus 1, 11, minus 1, minus 1, minus 1. So the new state will be 1 by 4 square root of 8. Everywhere this minus, and for this 1, 0, 0, it is plus 11. So now the probability of measuring 1, 0, 0 is its modulus amplitude square. So 11 by 4 square root of 8 the whole square, so which will become 0.9453. So for other things it became again reduced 1 by 16 into 8. So other states probabilities keep on decreasing, and for the targeted state it will keep on increasing. So actually up to here only we have to do as per algorithm, because now pi by 4 square root of n, it is only 2 iterations only we have to do. We can stop here and measure. So the 100 has the highest probability, so it will only mostly come out. It will come out with the probability 94.5% probability it will come out. So that we can verify then classically whether this is the correct thing, applying the C function. So Grover's algorithm always gives a probabilistic algorithm. There can be error, so you may have to repeat again with the same thing. But with very high probability, you will get the correct answer. Maybe you can verify it again using the classical computer. So in case of AES or any science, so this is how we check the key. So we will apply this Grover's algorithm. We will get something output with very high probability. Then you can classically verify whether that is the same key by applying the cipher with the same key and checking whether the input output is matching. If not, again you iterate again you get the output. So we have to iterate Grover only pi by 4 square root of n times. More you iterate, the probability start decreasing. So if I am again showing for you people to understand. So suppose I iterate again. So again I apply the C function. So the amplitudes now change up to -11. Here everything become -11. And then again I apply here. See, now the probability of 100 is going to 0.330. It is reduced from 0.94 so much to 0.330. So Grover, it will not keep on increasing and will go to 1. It is not like that. It will go only up to pi by 4 square root of an iteration. It will go increase and reach the maximum. After that, it will start decreasing. So why this is? Because that amplitudes actually we can represent as functions of sine and cosines. So cosine and sine theta form. So that in Grover's algorithm, what we are doing is we are increasing the angle so that the value sine, mod sine theta square will keep on increasing. So up to particular angle, when you reach pi by 2, it will become maximum. When again, if you keep increasing, it will start decreasing. Correct? So that is the same thing happening here. So if you will start from 0, it will start increasing. It will be like sine function. It is increasing, reaching up to some point. Again, if you iterate, it will decrease and it will go back to 0. So we need to iterate only pi by 4 square root of n times. Most with highest probability, you will get the correct key. Now we are going to apply this for the advanced encryption standard AES. So AES description already covered in first day. So I am not describing this. So it is a block cipher of 128-bit blocks and variable key size 128, 192, and 256. It has 10, 12, and 14 rounds according to the key sizes, and each round has a substitute byte, shift rows, and mix columns, and add round key. And there is a key expansion which will generate desired length of round keys using input keys, and it will be used. So I'm not explaining this. So now to apply Grover attack on AES, we have to implement the AES in a quantum computer. So how we will do a quantum implementation of AES? So I'm not giving a full details of that. So this is done in a paper by Marcus Grasel et al. So it is a paper in PQ Crypto 2016. You can see that actually I'm giving only some details of sub-bytes. So sub-bytes we need to implement inverse of the input. So that is alpha inverse we have to calculate. So alpha inverse, it is alpha to power 254. In that finite field, f2 power 8 they are calculating. So that we can calculate using this formula. You don't have to calculate alpha, alpha square, alpha cube, alpha raised to 4. Nobody will do like that. That is very complex algorithm. This is very optimized algorithm where you are square and multiply algorithm. So it is G algorithm. It is. So we calculating alpha into alpha square, then alpha and alpha square for square and square, then that one again square again. So we will keep on. We will first compute a square and a product, and it's squares and squares and squares and squares. So we will use only square circuit. So we will keep on square. Then we have to multiply. Square, multiply. That only is happening in this formula. So alpha into alpha square into alpha and alpha square fourth power. Then alpha and alpha square 16th. So this is alpha and alpha square fourth power. Again square. You will get like this. Again square like that. So square circuit will be keep on applying. So in squaring in f2x, that finite field g of 2 power 8, which is used in AES, is implemented in quantum circuit like this. So it uses so many C0 gates. You see, it is using so many C0 gates. So it uses 8 qubits A0 to A7, apply so many C0 gates. You will get output here A0 to A7. Here it will be square of the first, this input. So this is applied here. So this circuit you may have to call many number of times to compute this alpha to power 54 with a different input like alpha square, then alpha square, like that. So we can compute actually. So this implementation of alpha inverse actually needs 40 qubits and 3,584 T gates and 4,569 Clifford gates. So why it came is actually C0 gate is implemented using T gates and Clifford gates only. So instead of counting the C gates, they will C0 gate, they actually compute this T gates and Clifford gates. So one computation of alpha inverse requires 40 qubits and 3,584 T gates and 4,569 Clifford gates. So implementation of one 8-bit S box needs. Then after inverse, you have to apply some affine transformation. So that will not take any T gates. It is only Clifford gate only will be taken. So one implementation of 8-bit X box needs 40 qubits, same 3584 T gates, and because of affine, some is added actually 4569 Clifford gates. Here it is less. So there are many implementations. Again, for the S-box implementation, there are many implementations where they reduce the number of qubits instead of 40, they reduce to 10 qubits and all. But then it will make 9 qubits and all, and then but T gates count and all raised to 12,000. So different implementations are there. So here this people is this implementation. So this is a you can also think about your own quantum circuit to compute this alpha inverse, where you can use small number of qubits and less number of gates, something like that, optimizing number of qubits or optimizing number of T gates, because T gates are very costly to implement. So like that, you can also design your own quantum gate to implement this alpha inverse and this box. So they here in this paper, Grassel and et al, they considered this implementation, and so other blocks and all I'm not explaining here because of time constraints. So this is how they had done, and then for AES key schedule, it has taken almost this many gates. So AES 128, there are 176 NOT gate and 21,448 C NOT gate, 20,480 Toffoli gates, and this is T gates, depth of T gates, and overall T depth is 12,636. A number of qubits. For storage, they need 320, Ancilla means that extra qubits which is required for storing intermediate input output and all. That is 96. So you can see actually there needs lot of gates and the circuit is very complicated. So the key size also increases. And this is the full quantum resource estimation of the implementation of AES-128. So initialization, only 128 qubit is required, that for key. And for key generation, KSA, totally it is required this many T gates, 1,43,360, and Clifford gates is 1,85,464. So overall depth of the circuit is 12,626, and number of qubits required is 320. And there are 10 rounds, no? So totally for 10 rounds implementation. So T gates is 9,17,000 round, and Clifford gates become more than 11 lakh. And overall number of qubits required is 536. So total for AES-128 implementation, you need 984 qubits, and almost 10 lakh above T gates and 13 lakh above Clifford gates. And overall depth also 1,10,800 almost. Similar thing they calculated for AES, this is 192, 12 rounds. So it is taking 1,112 qubits and almost 12 lakhs T gates and 15 lakhs Clifford gates. And this is for AES 256. So 1,336 qubits are required, and it is T gate and Clifford gates are very high. So AES implementation itself is taking a lot of gates and qubits and all those things. We need a very large quantum computer. Now a Grover's algorithm to apply, we need that Grassel paper, they told we need at least 3 plain text ciphertext pairs to verify whether it is the correct key or not. So they are implemented 3 parallel implementations of quantum implementation of AES. So for one AES implementation, you need this many gates. Now you have to parallelly implement 3 AES. So this is also that function UF, which is used in the Grover's oracle, is like this. That is, it is using 3 different AES, and message are given as input for all 3 AES with the same key, and they compute the ciphertext. This ciphertext is verified with the given ciphertext. If it is matched, then that condition CS equal to 1 will be put, otherwise it is 0. After that, you have to recompute all the AES to reuse the circuit. So that is why this inverse is computed. So this actually we can calculate. You have to go through the paper. So total Grover search, that is to power that many iterations and it will come, no, 64. So for that 2 power 64 iterations along with the 3 parallel implementation of AES. So this is the number of gates that is required. So for AES 128, the number of T gates is 1.19 into 2 power 86. Number of Clifford gates is 1.55 into 2 power 86. Number of qubits is 2,953 with overall depth 1.16 into 2 power 81. Number of T gate depth is 1.06 into 2 power 80. So similar numbers given for AES 192 and AES 256. So as key size increases, number of qubits and number of gates and all increasing because number of rounds also increasing. So just keep. So then further optimization in the implementation of AES and all is done by some other people, that Samuel Jacques and all in EuroCrypt 2020. So they said only instead of 3, even 2, if you know only 2 plain text ciphertext pairs, then also you can get the output, get the correct, guess the correct key with very high probability. So this all actually reduced the gate count, and also further so many optimized implementations of S box, mixed column, all those things has come. Shift rows is nothing, just changing the gates. So but mainly mixed column and S box, so many other optimize implementations outcome. So people started using that and all. So here they have reduced the gate count to so much. So here they had given combinations of so many things they tried. So mixed column they implemented using one particular type of implementation, that is in place IP, and another type of implementation M Maximus papers implementation, and using one plaintext ciphertext pair or two plaintext ciphertext pair or three plaintext ciphertext pair. So each for AES 128, 192, 256 and all that. So if you compare this and the earlier work, now the gate count, number of qubits, all those things are reduced so much. So what is the conclusion is that what we learned. So people will say, no, as if you double the key size, you will get the security in quantum world for the symmetric ciphers. But it is not the only solution. It will not doubling alone will not give you the security. So we have to see the circuit depth also matters. So if AES is very heavy compared to so many other ciphers today, so its circuit is so much, its gate count and gate requirement, everything for implementation is so heavy that it is not nearby possible to implement it and attack it. But there are so many lightweight crypto systems which is being proposed nowadays and used in many places. So these things security has to be investigated in the same direction. So also there are people working on optimizing the circuit, quantum circuits for all these primitives like primitives implementation at S-box and mixed columns and other operations. So that space-time trade-off, number of qubits to number of gates. So that has to be again explored. Also, we can think about quantum implementation of other classical attacks. So there are so many attacks are also coming now, like quantum distinguishing attack and linear and differential cryptanalysis. So like that, different classical attacks can how we can apply in quantum, whether we can get any benefit or anything on that. So that also has to be thought of. And any quantum specific algorithms also attacks can also be think of. So there are so many scope of research in these lines. So there are so much work currently fast you can take up also in your as your project work or whatever it is. You can analyze that lightweight crypto systems for their security under Grover's attack or under any other attacks which is now coming up, and the resources required for a number of qubits and number of quantum gates required for this distinguishing attacks and linear and differential cryptanalysis. This all can be worked out. So these are the references I had mentioned. So Nielsen and Chuang book you can use for finding that details about qubit and quantum gates and basic quantum information theory and quantum computation theory, and about max depth and that security level and all those things you can refer to NIST call for a submission for PQC. And Grover search algorithm, this is Grover's paper 1996, a fast quantum mechanical algorithm for database search. It is purely mathematical, you can easily read. Only that computation of C function, that is only the quantum part of that. And this is the paper by Grassel and et al. So this is what paper first paper Grover applied to AES. So it is came in PQ Crypto 2016. And this is updation, latest updation, Samuel Jacques of all this Grover attack on AES. And law MC also they consider. So it is came in Eurocrypt 2020. And this is by Indian authors Ravi Anand and Arpita Mitra. This is in IndoCrypt 2021. So they given for a lightweight cipher, they have taken that grain 128. In that Grover they studied and quantum resource estimations are calculated. So similar line you can find out other similar ciphers. You can also work out on its security. So that's it, my talk. today. Thank you.
Thank you, ma'am. Participants, please note the link to submit the feedback form of this session is shared in this Meet chat. Kindly submit it without fail. Thank you. The session is now open for any questions.
Lakshmi, it's a basic question.
Hmm.
You told that a qubit has infinite number of states, no?
Yes,
Uh, if there are n bit, then it has 2 raised to n states, no?
No. Actually, it is that is the mistake people understand. See, if we take a qubit, it is not only on 0 and 1. It's on all combinations of 0 and 1. But when you measure, no, it will collapse to either 0 or 1.
Okay.
Understood? So it is in a combination of 0 and 1. But when you measure, no, you are measuring either in the direction of 0 or either in the direction of 1. See, when you measure the polarization of light, you keep that polarization, that thing in the one angle only, no? So in that angle, what is coming out only you are measuring. So that intensity and amplitude you are measuring.
So that
the same thing you cannot measure for the other vertical direction at the same time because it is already lost.
Okay.
Understood.
So because
but
of that
initial light is in a combination of
number of
yes.
Because
so
of that superposition.
Actual not disturbed system. If the closed system, they will tell no. The closed system is in all the superposition which we don't know. When we measure, we are actually disturbing the system, and it will be collapsed to one of the component vectors. So we will see only that much. It is not only 2 power n, it is combination of 2 power n. That is why it is called infinite. It has infinite states.
Okay.
It is actually the energy spectrum, no, from top to that. It can have any value between that.
Okay.
I think Abu understood.
Yeah.
Thank you, ma'am. Any other questions?
So the only non-invertible gate in the quantum circuit is the measurement. So measurement is a classical thing. So it is in an infinite combination of all the states. When you measure, no, which direction you are measuring, that corresponding with that amplitude, that probability, that thing will come out. That state will come out. So from there, you cannot assume what is the actual state of the system. Correct. So only that classical measurement is the only non-invertible thing. So once you've done that, its quantum nature is lost. So that is the main problem in the implementing a quantum computer. So you have to control also. So for that you need some classical intervention also. But then it will disturb the system. Then, but it just run on its own also. So this all things. Then some error will come. How to correct that error? All those things are only the bottleneck in this theory, which we cannot control actually.
So we are not getting the exact output, no? It's a probabilistic output only.
It is a probabilistic output. It is a probabilistic Turing machine model. So it is a probabilistic output. That's why I told him, Grover, you apply also that state is coming with the probability 94.94. Correct. It is not 1. So 0.94 means that other state also can come based on your measurement. It's not 0 for other state. So once you got the output, you have to verify it classically. Okay, I got the key as 001. So then I have to check whether ASMA apply, you apply and see whether the same input output you got or not. Then only your thing is complete. If it is not the correct, again, when you classically check the answer, if it is not correct, then you have to perform Grover attack again. So Grover, all the quantum algorithms, they will not give deterministic output with the probability 1. They are all giving probabilistic output only.
Okay, thank you, ma'am.
Okay, it seems like there are no more questions from the audience.
And
I think
Narose,
there is.
please wait. Priyanka is
Okay.
asking a question.
Ma'am, I am also working on quantum cryptography. I have some queries. Please, can you give me your email ID? So can I discuss
You
about
can
them?
ask G madam, she will.
Okay, Priyanka, I will share with you.
Okay, ma'am.
Actually, we are actually planning to start taking student trainees who can do project with us. They are project work. So if you can, only thing you have to be there in Bangalore, not to daily come to our office for at least 4 to 6 months. So many research problems and other things, project work, and so which we can immediately do. So that kind of thing can be taken up. Anybody interested can also contact me through VG madam. So any other questions?
I think there is no more question.
Okay, thank you, Abu Sar, for the question, and thank you, Lexi ma'am, for your valuable answers. Now, I request Mr. Ranjit Varghese, Assistant Professor, Department of Mathematics, St. Thomas College, to convey concluding remarks.
Good evening, all. It has been such an honor to be a part of this wonderful event. On behalf of the organization St. Thomas College Autonomous Thrissur, I would like to extend my heartfelt gratitude to our esteemed guest, Lexi Alexander, scientist, DRDO Bangalore. Today we had an opportunity to hear your thoughts, and this will surely be going to help us in understanding the cryptography, especially in the area of block ciphers. Thank you for an enlightened and entertaining presentation on topic block ciphers design and analysis. Thank you, ma'am. Thank you all.
Thank you, sir.
Very much.
With that,
Thank you for inviting me.
now we come to an end of the third day of our workshop. Let us remind ourselves to join tomorrow at 5:30 p.m. Thank you all. Good night.
Good night, all.